Hi everyone. Today I'll present Wheeler, a three-wheel input device for usable, efficient, and versatile non-visual interaction. I am MD Tauhidul Islam, a fourth-year PhD student at Penn State. My co-authors are Naushad Imran Ashikur Rahman, and the work was advised by Dr. Ruhul Amin and Dr. Said Billah. So let's begin. So this is Wheeler. As you can see, it's an input device designed for blind and low vision users who rely on assistive technologies such as screen readers to interact with computers. As you can see, Wheeler looks very similar to a traditional mouse, but it also works very differently. Unlike a mouse, Wheeler is stationary. The user doesn't have to move the device to use it. Wheeler has 3 wheels and 2 side buttons, as you can see in the picture. And all the 3 wheels can be rotated independently of one another. User places the index, middle, and the ring finger on the 3 wheels, and the thumb on the 2 side buttons. Of the 2 side buttons, one is bigger and mostly acts as the primary button of a mouse. The other button, that is the smaller one, mostly acts as the secondary button of a mouse. Wheeler also features audio and haptic feedback based on significant events. Based on multiple participatory design sessions with blind users, Wheeler has been designed iteratively, refined in each iteration. It works alongside other assistive technologies such as screen readers, which are commonly used by blind and low vision users. Based on the results of our study, Wheeler is highly efficient, usable, and versatile. So the first obvious question would be, why Wheeler? Why another new input device when there are hundreds, if not thousands, already available? Because assistive technologies such as screen readers have many major usability and efficiency issues, not the least of which is having to press too many keys when navigating from one UI item to another. In one of our prior work, we found that the more keystrokes it takes to navigate in an application for a task, the less usable and accessible it feels to the user. So this graph you see on the screen is from that work, which shows that the acceptable number of keystrokes for a blind users to perform a certain task. The graph says that the number of acceptable keystrokes is 3, according to most users. However, in reality, for most commonly used applications, the required number of keystrokes is much higher than 3. This graph shows the average number of required keystrokes in an app. The gray bars show the numbers when no shortcut is used, and the green bars show the numbers when every possible shortcut is used. For example, in Microsoft Word, it would take more than 17 keystrokes on average to navigate from one UI item to another. But the number comes down to 3.5 if someone knows all the possible shortcuts in an app. In reality, however, not even the most expert users knows all the shortcuts. Thus, they need tons of keystrokes to perform even simple tasks, and the perceived usability and accessibility of these apps remain questionable. This is exactly the problem Wheeler looks to address: speeding up hierarchy navigation. Let's consider this UI hierarchy as a representation of an application UI. Here, all the A's represent the first level items, all the B's represent the second level items, which are children of A's, and all the C's represent the third level items, which are children of B's. Now, Wheeler's first wheel can be used to navigate the A's, meaning if I rotate that wheel, it will move between the A items. Then, when a certain A is selected, this Wheeler's second wheel can be used to navigate the B's that are the children of A. For example, if A1 is selected by the first wheel, second wheel would rotate between B1 and B2. The same way, when a certain B is selected, Wheeler's third wheel can be used to navigate between the C's that are the children of that B. For instance, if B1 is selected by the second wheel, then the third wheel would rotate between C1 and C2. So the second wheel is automatically mapped to the first child of the item where the first wheel is at. So what I mean by that is, if the first wheel is at A2, the second wheel would automatically move to B3. The same way, the third wheel is automatically mapped to the first child of the item where the second wheel is at. Meaning, if the second wheel is at B2, the third wheel would automatically point at C3. This mode of operation is called the hierarchical navigation, or HNAV mode. Now let's compare Wheeler's HNAV mode against a traditional screen reader and a keyboard in an example. Let's say the user is trying to get to C8 from C2. So C2 is where the user is currently at. So the slide shows the screen reader and keyboard's performance on the left and the Wheeler's performance on the right. Screen readers have only one cursor, and it points at C2. And however, a wheeler, it has 3 wheels and 3 cursors for the same reason. The third wheel is obviously at C2 because the user is C2. And the second wheel cursor would be at C2's parent B1. And the first wheel cursor would be at B1's parent A1. This is the initial setup. So to get to the destination, the first move using the screen reader would be to press the up key. It would move the cursor from C2 to A1. As for wheeler, the first action would be to rotate the first wheel once because the final target is in a different subtree. Once the first wheel cursor moves from A1 to A2, the second and third wheel cursors automatically move to B2, B3, and C5, respectively, for the reasons I just explained. Next, using screen reader, the user would press the up key again on the keyboard to move from B1 to A1. As for wheeler, the user would rotate the second wheel once. This moves the second wheel cursor from B3 to B4, while the third wheel cursor moves automatically from C5 to C7. With screen reader, the user presses then the right arrow to get to A2 from A1. For wheeler, the user rotates the third wheel once, which takes the target cursor from C7 to C8, thereby completing the navigation within 3 actions. As for the screen reader, we have to still make more moves, the next being a down arrow to move from A2 to B4, then another one from B4 to C7, and then finishing up with the right arrow from C7 to C8. Thus, the screen reader keyboard-based interaction here takes 6 actions in total compared to 3 with wheeler. Now let's see how a user would use wheeler's HNAV mode in real application like Microsoft Word. Here, the user wants to insert a text box with some text while the user is currently at the home ribbon. So let's see how it goes. Unfortunately, the audio was not playing, so I'll just play it in my speaker. Okay.
Insert tab selected. Group pages. Group tables. Group illustrations. Group media. Group links. Group comments. Group header and footer. Group text. Text box.
So one more thing, the audio you hear is from wheeler's own audio and not using any screen readers. So to summarize HNAV mode, the 3 wheels help navigate the first 3 levels of an application in a hierarchy independently, and the primary and the secondary buttons activates or deactivates currently selected items at the third wheel's focus. I have talked about wheeler's efficiency and the usability over screen reader keyboard-based interaction so far. Now let's take it to get its versatility. How else can we utilize the 3-wheel design of wheeler? For starters, here is a summary of repurposing the wheeler device for 2D cursor navigation. The first 2 wheels would move the cursor horizontally and vertically, and the third wheel for adjusting cursor speed, while the 2 buttons would simulate the left and right click of a mouse. So here's the visualization of what will be happening. So the first wheel will be moving the cursor horizontally, the second wheel moving the cursor vertically, and the third one to just adjust the speed of the cursor. Here's an example of the 2D nav mode in action. Here the initial cursor location is shown in green arrow, and the final target location is shown using the yellow arrow. Note that the target, that is Microsoft Edge's approximate location, with respect to the top left corner of the screen is given. You can see that it's around 22% from left and 68% from top. So let's see how it goes.
78% from left, 16% from top. 42% from left, 16% from top. IntelliJ idea February 3rd, desktop. 43% from left, 66% from top. 27% from left, 66% from top. Microsoft Edge.
So the user was holding the primary button for 1 second to get feedback on where the cursor was. So that's how they get the feedback on the cursor. And this mode of wheeler, which one can use to manipulate the cursor in 2D space, we call it 2D navigation or 2D nav, in short. So this is for wheeler spotter. You can see the assembled version on the left and the individual 3D printed components on the right. And this is wheeler internal circuit connections. I really can't go into any more details for the sake of time. Please stop by at our booth during the demo session today, which will be 6 to 9. Next, the evaluation of Wheeler. To evaluate Wheeler's usability and effectiveness, we conducted a user study with 12 blind participants. The participants performed 2 tasks. Task 1 was designed to evaluate the HNAV mode. In the first condition, participants navigated to a given target using a keyboard and a screen reader. The second condition, participants navigated to a target using Wheeler only. In task 2, which was designed to evaluate the 2D nav mode, here we didn't have a baseline, so just one condition. There is no baseline as blind users do not visually navigate 2D space because the tasks requires visual feedback from the cursor, which the current systems do not provide. In task 2, participants needed to navigate to a given target on the screen given its approximate location. Here are the results from the study. We see a significant 40% improvement in task 1. In other words, navigating app hierarchies using Wheeler's HNAV mode is 40% faster compared to navigating with a keyboard and a screen reader. As for the 2D nav mode, the users were able to, or not able to manipulate the cursor in 2D before, but they could now using the mode. These four figures demonstrate the learnability of Wheelers in 2D nav mode. I'm not going to explain them extensively, but as I'm running out of time, but the key idea here is that the metrics which correlate to the difficulty of completing a task, such as completion times, the number of times a cursor location is probed, or the number of times the cursor speed is adjusted, all of these go down with time. So it means that it gets easier to find a target in 2D nav mode. So to wrap up, complex hierarchy navigation in an application is a demanding task for blind and low vision users using keyboard and screen readers, where they have to make around 25 to 30 keystrokes at times to move from one UI item to another. That's why we introduced Wheeler, a 3-wheel input device that can enable blind users to navigate app significantly faster, which also offers additional benefits such as 2D mouse-like cursor navigation. Thank you, and I'll be happy to take questions.
So, since we're waiting for a question, and we are kind of out of time, so I will just have one question to you. So in the paper, you mentioned a possible extension to VR, where it's totally different computing platforms, 3D and so on. So just do you have any thoughts that you can share with us here?
Yeah, sure. Actually, we are already working on a different project that works with regarding visual accessibility in VR. So it has to do with when you are holding a controller in VR, you have no sense of where the cursor or the orientation of your cursor is. So one possible way would be like announcing where your VR controller is. So even then, moving a controller in 3D, I can only assume that how tough it would be for blind users because we saw how tough it was in 2D. So one idea could be like if you can allow the user to, move the cursor in 3 dimensions using the 3 wheels, like it would be much more controllable for them. Maybe you can add another extra button for adjusting the speed, something like that. It's still under consideration, so maybe we'll see what happens in the future. Thank you for the question.
So I'm Matthias Lisbeck from Aarhus University. Don't be fooled by this shirt. I have just one question on the scalability of it. Since you have 3 wheels, that assumes that at most a 3-level design, right? What if you had just 2 wheels and one for controlling the depth of the tree and another for controlling the horizontal index in the branches? What would that mean? Do you have any comments on that?
Just to make sure, thank you for the question. Just to make sure I understand it correctly, you are asking what would happen if we have just 2 levels or 4 levels, right?
No, if you have 2 wheels, where one wheel controls how deep it goes in the tree, and the other wheel controls how horizontal it is at that depth you choose with the first wheel. So you go down to level 3 by clicking it 3 times with the first wheel, and then you go to leave 3 by clicking the second wheel 3 times.
I see.
What would happen then?
Okay. That's actually a very good question. So what would happen is, like if you're trying to use just one wheel to go down, you need a definite order. You can do that in a list. If going down is a one-dimensional movement, you have just one-dimensional list, then it's defined. But what happens in UI hierarchies is one component can have multiple children. So whenever you're pressing the right key, which children should the cursor next go to? So that would be a confusion. But I think what you proposed could be a good idea, so I'll definitely look into that. Thank you.
Thank you.
Right. Let's thank everyone again for the talks.